So इसमें क्या क्या किया था? We had talked about complexes. We had talked about some specific, very specific complexes that if you have copper with water, that's blue. Copper gets surrounded by OH ions, that's a pale blue precipitate, forms a precipitate. Copper getting surrounded by NH3, that's a dark blue solution. Copper with HCl -1 ligands, that's greenish yellow. The cobalt complexes, they were exactly the same, but they had different colors. We wrote down equations for ligand exchange reactions where copper pe agar OH ions are coming in, then that's forming a copper hydroxide precipitate. Then it was if NH3 comes in, then the ligands they get substituted by NH3. Cl lines to Cl lines. Then we talked about the stability constant, and I told you that it's the equilibrium constant for a ligand exchange reaction, specifically for the formation of a complex ion in aqueous solution. That means that initially the ion, the metal is involved or it's forming a complex with water, and then it ends up with another ligand. And so it's the equilibrium constant for this K stability, which means that if you got a big value, that means ligand exchange will happen. There's going to be more products compared to reactants. If the K stability value is small, then that means lesser products, less likely for the ligand exchange to happen. Anyways, this is where we ended up last time. Okay, I told you that every transition metal, it's got a d subshell which is incomplete. That's how your d subshell looks like. Then we talked about the fact, okay, 1 second. I said, then we also talked about the fact that if you look at the d subshell, that there are like 5 different types of d orbitals which can be broadly distributed into 2 groups. One of them is that the d subshell electron density lies between the nucleus, which is your dxy, dxc, dyz orbitals, and then you have the 2 orbitals where the electron density lies exactly on the axis. And so you had a bunch of d subshells which were on the axis, lying on the axis, and you had a bunch of d subshells that were actually lying between the axes. So I told you that when you have a copper ion, the copper ion, it loses the electrons in the 4s, the fourth shell, the outer shell electrons are gone. And these are your inner shells, inner subshells. And if you look at the D, then the D is incompletely filled. That means that the D has, there were 5 orbitals. Some of the orbitals were lying on the axis. Some of the orbitals were lying between the axes. This was just a rough sketch. Okay, बहुत rough sketch था, which showed all the D orbitals together. So there was electron density lying between the axes, electron density lying on the axis. So I explained to you that when a metal ion forms a complex and when it attracts these ligands, so some of the d subshells orbitals, it becomes harder to keep electrons because there's too much repulsion. Okay, water agar axis pe aa raha hai na, its lone pairs are coming in, then it would be much harder to keep the electrons in these blue orbitals over here, and it would be a lot easier to keep electrons between the axes. Blue wale mein electron rakhna mushkil hoga. Middle part mein electron, keeping the electron would be easier. So what happens is that your d subshell, which was degenerate, that meant they were having exactly the same energy. They split into 2 different energy levels. The ones on the axis becomes harder to keep electrons, and the ones between the axes easier to keep electrons. And there's an energy gap. And I told you, I explained to you that your electron can actually switch. Like if you have this electron, then this electron can actually, I mean, it would like to be present between the axes because it would be a lot harder for it to be on the axis. But this electron can switch and it could jump and go into a higher energy orbital, d orbital. But for that, it would require a lot more. I mean, this electron has to be a lot more energetic because it's going to face a lot of repulsion over here. So your electron can actually move between the 2 states, the low energy state and your high energy state. And there was a specific energy gap. The electron is supposed to gain a very specific amount of energy. There's nothing special about this. The electron absorbs that specific energy, moves to the higher energy d subshell, but when it does that, it absorbs a frequency that belongs to the visible spectrum. So every atom I explained to you goes into excited state. But the thing with transition metals is that transition metals absorb energies that belong to the visible spectrum, which is why you're able to see them as colored. Or वो मैंने explain किया था, you always see a complementary color. That, for example, if there's a bunch of frequencies that are falling onto the transition metal, and there are all sorts of frequencies around you, if it absorbs the radio waves, then obviously you won't see any difference because you don't see the radio waves to begin with. Lekin when the light hits and it absorbs blue light, so the light that is getting reflected and going into your eyes, that's if it doesn't have blue light, you're going to see that missing. And the color that would appear to you, it would appear red to you. It's not going to appear blue to you, okay, because the blue light is actually missing. So you always see the opposite color. Is that clear? ये clear है सारों को? इसको हटा दें. अच्छा, so you're going to write an answer for this, and you're going to write an explanation. So there are two questions which need to be answered, and the first one is, you're going to get exactly the same question. Okay, so the first one is, why are transition metal complexes colored? Transition metal complexes colored, and that's your first question, and it has to be a very specific answer. So what you're going to write about this is that due to repulsion from lone pairs on ligands, so due to repulsion from lone pairs on ligands, what happens to the d subshell is the d subshell splits into two energy levels. So it splits into two energy levels. Electron from the lower energy d subshell, so your electron from lower energy d subshell or d orbital, it gains energy and moves to higher energy d orbital. Then the next thing is you're going to talk about delta E. So the energy gap, that is delta E, matches frequencies that belong to the visible spectrum. So that belong to the and you're going to write that since energy is proportional to frequency, Hence, a complementary color is seen. Okay, that sums up your answer. Okay, that's going to be your specific answer for this. So D subshell split color, it's going to be a 3-4 mark question normally. And so due to repulsion from lone pairs or ligands, the D subshell splits into 2 energy levels. Electron from the low energy d orbital gains energy and moves to the high energy d orbital. And the energy gap delta E matches frequencies that exactly belongs to the visible spectrum, since energy is proportional to frequency. Hence, a complementary color is seen. Okay, so idea clear? Is this clear to everyone? Umar, clear? Sana, is this clear? Sidra?
Yes, sir.
Yes, sir.
So now, similarly, the next thing is that so complementary color seen. Then you're gonna get another question, which is why do different complexes have different colors? Yeah, that's the other question that's going to be asked. So why do different complexes have or similarly, like if you change ligands, why does the color change? So I mean, the same thing will be that the same thing over here will be that when you have different ligands, you have different colors. So the answer to that one is that what happens is that if you have a different ligand, it is going to exert a different amount of repulsion. So different ligand lone pairs, they have a different charge density. So ammonia lone pair and a water lone pair, they're not going to be exactly the same. So they have a different charge density and will exert a different amount of repulsion. A different अब उससे क्या होता है कि if they exert a different amount of repulsion, so delta E, which is your energy gap, changes. So the energy gap between the orbitals changes. And since the energy is proportional to frequency, a different frequency is going to be absorbed. So a different frequency gets absorbed from the visible spectrum. So from the visible, that's your second answer. So you're gonna get two typical questions, and those are your two typical answers for those questions. Okay, clear here? सारों को क्लियर है वैसे, है ना सना? क्लियर है सारों को?
Yes, sir.
Yes, sir.
अच्छा, अब ये कि so that's your second question, and usually it's just these two questions. That's about it. Exactly the same questions. Now, so that's all about the colors of transition metals. The other thing that we're going to do is we're going to talk about isomerism and a bit more about ligands. Okay, so the next thing apart from colors, okay, those are your two answers for colors. The next thing is, actually, sorry, एक very important चीज उस पर रहेगी, which is this one. So how does the D subshell split? Remember that you've got your dxy, dxz, and you've got your dyz. So then you have your dx square minus y square, and then you have your dz square. So now about the splitting pattern of the D subshell. Now that's your degenerate D subshell. Every orbital has exactly the same. It has exactly the same energy level at the moment. Okay. So right now every orbital has exactly the same energy level. Now what's going to happen is that it's going to split into two different sets of energy levels. But there's a difference between an octahedral and a tetrahedral complex. Now we studied octahedral complexes. This was an octahedral complex. Now when you have an octahedral complex, what happens is that all the lone pairs are attacking the copper ion or attaching to the copper ion on the axis. So it becomes harder to keep electrons in the blue orbitals, which are on the axis. Okay. So in octahedral complex, the ones on the axis, it becomes harder to keep electrons. So dx square minus y square and dz square have a higher energy level. And you've got your dxy, the ones between the axes, dxz and dyz. So those are your lower energy level orbitals. Now, but that's true for an octahedral complex. So that's true for an octahedral complex. So let's go. Okay, so that's true for an octahedral complex. But what happens in a tetrahedral complex is, okay, things are opposite. In tetrahedral complex, it's exactly the opposite. That it's harder to keep electrons between the axes, dxy, dxz, and dyz. And it's actually easier to keep electrons on the axis. Yeah, that's what's going on in a tetrahedral complex. And there's a reason for that. And the reason is that ये जब आपके पास tetrahedral complex होता है ना, तो the ligands are not approaching on the axis actually. They're actually, like, if I show you an octahedral complex, sorry, tetrahedral complex. So unlike an octahedral complex, where's your tetrahedral? Acha, this one. So unlike an octahedral complex, in a tetrahedral complex, the ligands are not approaching on the axis. They're actually coming at an angle of 109.5. So therefore, it's actually easier to keep electrons on the axis, and it's more difficult to keep electrons between the axis. Okay? So ये बात clear है कि tetrahedral में it's the opposite. I mean, it's exactly, the concept is exactly the same, except that the splitting is exactly the opposite. Is that clear? ठीक है, सारों को clear है? Sana, is this clear? Nasib, Anna, Risha, clear?
Yes, sir.
तो बस ये थोड़ा सा ना make sure you remember this small point. अच्छा, anyways, the next thing, now moving on. So moving on, what's going to happen next is, okay, you've got we're going to talk about bidentate and monodentate ligands, and we're also going to talk about isomerism. Okay, so what's a monodentate? You have your bidentate, and you even have polydentate ligands. And later on, we're going to talk about isomerism. Now, dentate actually means teeth. It means lone pair, basically. So think of dentate as lone pairs. So a bidentate ligand is, by definition, one that can form two dative bonds with a metal cation. It can form because it's got two lone pairs. So I'll just, giving the definition of bidentate means that, so bidentate ligand. So it's something that forms, it's capable of forming two dative bonds with a metal cation. अच्छा, इसका syllabus खोल लेते हैं because you have, specifically we have to cover ये वाला, नए वाले में एक दफा confirm कर लेते हैं. You just have to cover 2 or 3 cases. ठीक है, so अच्छा, this one. So understand and use the terms monodentate. We already did most of them. Cn-1, just remember, is another dentate. Sorry, another ligand. Now, bidentate, you have to know about these two: C2O4 2- and diamine, ethane diamine. And there's a polydentate ligand, which is eta. You don't even need to know what the structure is, but we'll cover the structure as well. As I starting with the first one, as a monodentate, we already aware of what a monodentate is. ठीक है, water NH3 बल्कि यहाँ पे लिख देता हूँ कि those are your normal ligands capable of forming just one. So you've got water, NH3, Cl-1. So they are all, I mean, they have more than one lone pair, but the ones that can form dative bonds, that's only one. Water has two lone pairs, but only one of them can form a dative bond. And we can add Cn-1 as well to this list. Achha, but bidentate, what's a bidentate ligand? So a bidentate ligand is, I'll take the example of copper again. So if I have copper 2+, the copper 2+ is going to have, it's going to have 6 sides. So there's going to be a top, and there's going to be a bottom, and there's going to be a bond that would be coming out of the page. These are all your axes. There's going to be one going into the page. So we've got another one, and so coffee. So that's those are your 6 sides. Those are your X, Y, and Z axis. And a bidentate mena, you have these examples. You've got the examples of diaminoethane. So we'll take that example first. Now it's basically a bigger molecule, And that bigger molecule has two lone pairs. So there's an NH2 and there's another NH2. The only thing is that they are connected together by a carbon chain. There's a CH2, then there's another CH2. So that's what a bidentate ligand looks like. That it's a big molecule. So one side goes and bonds to the or gets attracted to the copper ion from one side, and the other one goes and gets attracted to it from the other side. So you'll be very frequently asked to draw exactly this one. So you've got NH2, NH2. Technically, you can be asked to draw any one of them. अच्छा फिर यहाँ पे भी ना there's going to be NH2. And there's a carbon chain that's connecting them together. So is this clear what a bidentate ligand is? Ye clear?
Sir, on the left side, is the CH2 combined together?
हाँ मतलब CH2 ये वाले ना हाँ connect वो सारे connected हैं all together. ठीक है, so it's a big molecule and all of this is one molecule, but it's हो ये रहा है कि वो एक साइड से आके N उसका bond करे datively, the other one is getting attracted. So it's like 6 ammonias, but except that they kind of connected together by a carbon chain. नहीं, all of them are not connected. ये चीज connected है कि एक सेकंड, not all of them. कि अगर मैं ये molecule है ना, this is one molecule, right? And this molecule goes and gets attracted, और वो it gets attracted, its lone pair gets attracted to copper 2 plus ions, और वो दूसरी साइड से ना its lone pair gets attracted to copper 2 plus as well. ठीक है, clear है?
Yes, sir.
तो ये bidentate ligand है, and there could be another one with C2O4 2 minus, ठीक है? So you could have, actually you could have another one, ये मैं रब कर देता हूँ. So you could have another one where you can have C2O4 2 minus as the bidentate ligand. So C2O4 2 minus is this thing. कि उसमें ना there's a C2 or oxygen -1 होता है, and there's another oxygen which is -1 and double bond O, and you've got a double bond O. तो वही हो रहा है कि इसका जो lone pair है ना, it's getting attracted to copper, and this lone pair is also getting attracted to copper ions. ठीक है, then you have another one where you एक और आ जाएगा. ठीक है, so you got 2 C's, double bond O. So this is the one which has lone pairs. It's got a -1 charge. So you have to remember this specific example. Same thing here. So that's another example of a bidentate ligand. ठीक है, तो ये so that's kind of one molecule but forming 2 dative bonds. Is that clear?
Sir, why does O have -1?
नहीं, वो तो आयन था ना, C2O4 -1 was an ion. उसके साथ it's a dicarboxylic acid ना. Carboxylic acid क्या होता है? It's like if you have a carboxylic acid, एक सेकंड में इसको
Understood, sir.
ठीक है मतलब वो कार्बोक्सिलिक एसिड था मैं फिर भी एक्सप्लेन कर देता हूँ इफ यू हैड अ कार्बोक्सिलिक एसिड डबल बॉन्ड O OH तो वो somewhere down the line H must have been lost so when the H is lost it becomes a -1 so ये जो है ना ये जाके इसका lone pair gets attracted to the copper 2 plus in the middle ठीक है so but it's a bidentate ligand which means that it's capable of forming two dative bonds ठीक है so that's your bidentate ligand and that's about it ठीक है बस यही पढ़ना है इसमें and you're going to get exactly maybe they might give you some other bidentate ligand but usually it's the same bidentate ligand you get exactly the same one ठीक है specifically these two ethane dioate and diamino ethane इसका नाम भी लिख लेते हैं this molecule is diamino ethane it's ethane with two amines and this one is ethane dioate ethanoic acid tha, but like it's got di because there are two of them so it was ethane dioic acid but it lost an H+1 so it became ethane dioate ठीक है that's the ethane dioate ion अच्छा फिर इसके बाद है कि so I'll just give you examples of other polydentate ligands and I'm going to talk about ETA as well now अच्छा now your metals I'll give you other examples that are irrelevant most likely no one is going to ask you about them ठीक है but just to give you an idea इधर मैं लिख भी देता हूँ some other irrelevant examples so you don't really have to specifically know about them but just to give you an idea about what bidentate tridentate tetradentate etc so one of them is the heme group okay hemoglobin in your red blood cell that's kind of the heme group is kind of a polydentate a pentadentate ligand probably okay if you look at your hemoglobin molecule you'll notice that your limit say अच्छा what you'll notice about it is कि अच्छा what you'll notice about this is that there's this iron that's right in the center ठीक है middle में ना there's an iron and that iron probably has I think it has a 2+ charge it has a 2+. Common one is 2+ actually let me just double check the iron oxidation state in hemoglobin it is +2 3+ बहुत मुश्किल है अच्छा so it is 2+. So iron over here is 2+, right? So this is in your red blood cell it's a pentadentate ligand you've got this big molecule and us big molecule के different parts of that molecule are datively bonding to it it's forming an octahedral complex there's an N lone pair coming from one side there's an N lone pair coming from the other side N lone pair one एक नीचे से आ रहा है bottom से आ रहा है one side is open that one side is the one that's actually used to absorb oxygen okay that is where oxygen gets absorbed okay so what you get on this side is on the 6th side oxygen comes in and it comes in with its lone pairs and it gets attracted to the iron in the heme group okay idea clear is this clear that what a pentadentate ligand looks like is that clear और ये आपकी
Yes, sir.
और जितने भी मेटल आयंस है ना आपकी बॉडी के अंदर they are all in the form of these complex ions ठीक है they're stuck between I mean there's a big molecule and they're kind of stuck in the middle of that big molecule forming dative bonds अच्छा इसी तरह you can have ETA का example है, that is important. Okay, so we'll just do ETA EDTA, and I think it's got a charge of 2 minus. So this one is a hexadentate ligand, which means that it's capable, like one molecule is capable of forming 6 dative bonds. So this one is hexadentate. Or इसमें क्या होगा? EDTA. Now you'll definitely not be asked to remember this or draw this. You just need to have an idea about what this is. So ETA ligand complex, first thing, the molecule. It's got a charge of 4 minus. So this is what it looks like. It's I mean, this is the actual shape of the. ये का नजर आ रहा है, ये इतना clear नहीं है, एक second. I guess this one. तो ये सही है. अच्छा, so you've got this thing, and if you look at this thing, it's a big molecule with a lot of oxygen and lone pairs, etc., from all sides. Okay, there's a lone pair on the top. There's a lone pair over here. Lone pair with N over here. There's another lone pair with N. All these lone pairs are getting attracted to the oxygen. So that's your ETA molecule, and it's a hexadentate ligand, which means that आपके पास, अच्छा, it's a hexadentate ligand, and that kind of means, so that what that means is that one big molecule is forming 6 dative bonds with the metal ion that's stuck in the middle. ठीक है, clear? Is this clear? Example clear है? और ये थोड़ा याद रख लेना कि इसका जो charge है ना. So obviously, definitely, they're never going to ask you to draw this. ठीक है, कभी कभार ना equation बनी हुई मिल जाती है. So you might be, but you should have some familiarity with this. Otherwise, not the drawing is not that important. Just the idea that it's a hexadentate ligand. Is that clear? ठीक है, सारों clear? Alicia, Seep, Sana, Sidra, Omar, clear है सब?
Yes, sir.
तो बस ठीक है. So we'll do isomers tomorrow then. ठीक है. यहीं पे अभी बस वो है कि colors का reason and the different types of bidentate, tetradentate, pentadentate, hexadentate ligands. ठीक है. और उसके याद रखना कि syllabus में the important ones is ETA and this one. These are the only two that you'll be asked to draw this. This one you'll definitely not be asked to draw this. चलिए ठीक है, कल बात होती है. ठीक है. Okay, everyone. Take care. Allah Hafiz.
Graphic.